Good morning, beautiful people, and welcome to Physics 210 class again. I welcome you once again to the class. This is our second class for the semester, and for this class, we'll be talking about one of the basic components in circuit, and that is the capacitor and capacitance. Remember last class we discussed resistor and resistance. So we are moving on again to one of the basic components in electronics, which is the capacitor and capacitance. And by the end of this session, by the end of this class, the basic things I feel you should be able to understand and basic questions you'll be able to answer are that you should be able to differentiate between the terms capacitor and capacitance. You should be able to state the different types of capacitors that we have. You should be able to differentiate between the two capacitor combinations with appropriate diagram. And also you should be able to solve simple circuit calculations on both the two combinations that we have for the capacitor. So I'll be moving on. The first thing I'll be talking about is our capacitor and capacitance. When we say a capacitor is a two-terminal electric component. A two-terminal. When we say two-terminal, which means it has a positive side and a negative side. Just like our cell. So that is two terminal, two sides, two ends. That is what I mean. So when you say a capacitor will always have two ends, one at the left side and one at the right side, just like our resistor. So a capacitor is a two-terminal electric component which has the ability or the capacity to store energy in form of electric charge. Now one thing I need you to understand here is that there's difference between your resistor and your capacitor. Both of them, what they do in a circuit are different. So you must be able to understand and differentiate the work, what both the resistor and capacitor does in a circuit. So a capacitor now, what they do mainly is that they store energy in form of electric charge. And now that is a capacitor. Now that particular component is a capacitor. Now capacitance is now the ability of that your component, ability of that your capacitor to store the energy in form of the electric charge. We said that a capacitor is a two-terminal electric component. That component that will store the electric energy is a capacitor. Now the ability of the component to store the energy in form of the electric charge is the capacitance. So you must take note of the difference between both. In other words, the capacitance is the storing ability of the capacitor. Can you see? The storing ability of the capacitor. Now, the charge that is being stored, the accumulated charge in the capacitor, is directly proportional to the voltage across the capacitor. And that is where the formula Q is directly proportional to V now comes in. Now remember when we had Ohm's law, we said that our V is directly proportional to I. Then we now incorporate and bring in a constant of proportionality, which was capital letter R. Now the same thing applies here. Our Q is directly proportional to V. So we need to introduce a constant of proportionality here as well, so that we can eliminate the proportionality sign. And our constant of proportionality in this case is C, capital letter C. So we now have Q equals CV. So we can always, walk around and play around with Q equals CV, depending on whatever we are trying to solve, depending on whatever we are trying to, the formula we are trying to use, what we are trying to get. So in this case now, we can actually say that our C equals Q over V, and we can also say our V as well equals to Q over C. You see that C is the capacitance of the capacitor, which has the unit in farad. You might see microfarad, you might see picofarad. So as long as it is in farad, you are talking of the capacitance of a capacitor. Now these two diagrams here, they are the basic. This is just a typical diagram of a capacitor. On your left side, the one in blue, that is a capacitor. So if you have any electrical device in your homes, and maybe perhaps you are trying to check whatever issue is happening with it, if you open it up and you see this type of components, the diagram you are seeing right now, this blue diagram, that is a capacitor. And in circuit diagrams, if you see a diagram that look like the one to your right, having these two straight lines, that is the symbol. So the symbol is the one to your right, while the capacitor itself is the one to your left with blue diagram. So we have different types of a capacitor. We have different types of capacitors. We have the film capacitor, ceramic capacitors, electrolytic capacitors, and variable capacitors. Majorly, these capacitors are named according to the material used for their dielectric material use. That is what they are being named. That is what the naming comes from. That is where the naming comes from. So we have to understand that there are different types of capacitors. Now these are the four that I give to you. So by the time you check your course materials, you'll see the basic explanations there. So we have capacitor combination. How our capacitors are being combined in circuit, just like we have in our resistor. Our capacitors can also be combined in series and also in parallel. So we have both series combination and we have parallel combination. Our capacitors are capacitor combination is connected to a battery or to a cell. So if you're in any material, or maybe you are trying to check whatever on net and you see cell, we still refer to as the battery. So capacitor combination is connected to a battery to apply a potential difference V, the voltage. So the essence of that battery is for it to supply the circuit with a voltage, which is the same thing as a potential difference, and charge the plate. The potential difference, or the voltage, will charge the plate, and the resulting charge is what we symbolize as capital letter Q. So two frequently used method of combinations are parallel and series combination. So first of all, I'll be talking about the parallel combination of capacitors. Now when you have two terminals, the two terminals of a capacitor, when you have them being connected to each terminal of another capacitor, those type of arrangements are said to be in parallel combination. They are said to be in parallel combination when two terminals of one capacitor, when the two terminals of one capacitor are connected to each terminal of another capacitor. Let me take that again. Two terminals of one capacitor is connected, or let's say are connected to each terminal of another capacitor. The capacitors are said to be connected in parallel. Now, for parallel combinations, the same potential difference flow through. For parallel combination, we have the same potential difference flowing through, but different charges. The voltage is the same across all capacitors that are linked in parallel. When capacitors are connected together in parallel, the total or equivalent capacitance CT is equal to the sum of all the individual capacitances in parallel. Now I need you to understand something. It makes understanding this thing easy. Now One thing I need you to do is try to compare, try to see the relationship, the differences between parallel combination of resistor and parallel combination of capacitor. The same way the parallel combination of resistors look like in circuit, the same way the parallel combination of capacitors as well look like. But when you are trying to get the equivalent capacitance is the formula to use is different from how we get our equivalent resistance. For equivalent capacitance, the sum of all the individual capacitances are done to get the equivalent capacitances. Take for instance, you have a circuit diagram having capacitance C1, C2 and C3, and you have to get the equivalent capacitance. In this instance now, your CT, which is the total capacitance or equivalent capacitance, you just have to sum those three capacitance together, which will now be C1 plus C2 plus C3. So for parallel combination of capacitors, your equivalent capacitance is just the sum total of all the capacitances you are having. So this one is different from what we did for parallel combination of resistor. Now look at this circuit diagram shown above. What you are seeing down there with V, that is a battery. That is a battery having the positive terminal and the negative terminal. Now connected to that battery are your capacitances. There are 4 capacitances connected to that particular battery. These capacitances are connected in parallel. So anywhere you see this type of connection, this is a parallel connection. These are parallel combinations of capacitances. And when you need to get your total capacitances, or the equivalent capacitance rather, you just have to do your C1 plus C2 plus C3 and plus C4, and it gives you the total capacitance in that particular circuit. Now this says when adding together capacitors in parallel, they must all be converted to the same capacitance unit, whether it is microfarad, nanofarad or picofarad. Now this is very, very important. When you are trying to get your equivalent capacitance, all your capacitors must be in the same unit. If perhaps you are having 2 microfarad for C1, you are having 3 nanofarad for C2, you are having 3 microfarad for C3, and you are having 6 farad for C4. You can see that all the units are not aligned. They are not the same. Microfarad is different from farad. Micro is 10 series per minus 3, or minus 6. Yes, minus 6. That is micro. So if you are having 2 microfarad, that is 2 times 10 per minus 6. So it is different from 4 farad or 6 farad. Can you see? So adding 2 plus 4 is different from adding 2 times 10 per minus 6 plus 4, which shows that you need to be careful whenever you are dealing with any of these components, either the resistor or the capacitor or the insulator. Make sure that all the units are correct, they are the same. It makes getting your total or your equivalent capacitance very easy. By the time all your units are the same, you can try to convert everything to microfarad. You can try to take everything to farad, so that all the units will be the same thing. Now we can also define total capacitance of the parallel circuit from the total stored coulomb charge using Q equals CV. Now remember I said it before that the same voltage for a parallel combination of capacitor, the same voltage flows through. All the capacitors in that particular circuit will be having the same voltage. So if you are trying to get your total capacitance from your charge, remember that our charge is CV. Now that V, for the first, maybe you're having 4 capacitors now, just like the previous circuit diagram I showed you. You're having C1, C2, C3, C4. For charge, for capacitor C1, the charge will be C1V. Then you have C1V1, C2V2, C3V3 plus C4 V4. Yes. Now in these instances, the same voltage is flowing through, which means the voltage you're having for V1 is same voltage for V2, same voltage for V3, and the same voltage for V4, your V4. Now see those V's, since they are all the same, eliminate them. You will be left with your C1 plus C2 plus C3 and plus C4. So which means even if you are trying to get your total capacitance from your charge, you will still come back to having the same thing. So either you get it from using Q equals to CV, or you just do directly from C1 plus C2 plus C3 plus C4. You will be having the same total capacitance for your parallel combination. Now let's take an example. Let's take an example on parallel combination. This says, using the circuit diagram below, calculate the equivalent capacitance, the charge, and the potential difference across each of the capacitors. Now the first one, C1 is 8 farad, C2 4 farad, C3 2 farad. Now the first thing is you take note of those units and you realize that they are having the same unit, so you don't have any problem with your unit. Now for a parallel combination, we already said it that our capacitances, the equivalent capacitance for parallel, you just add all the values you're having for your capacitances. So you have your C equivalent to be C1 plus C2 plus C3. So by the time we had all the three values, we'll be having 14 farad. So that is the first question being solved. Now the second question says the charge across each capacitors. The charge. The first thing that you must check in the circuit is that we're having our V. The potential difference across is 10 volts. 10 volts. So you have 10 V there. Then to calculate charge, which is Q, Q equals CV. So for each of the capacitors, we need to calculate the charge for each of the capacitors. Now for capacitor 1, which is 8 farad, we have Q equals to C1V. Our C1 is 8 farad and our V is 10. So we have 8 farad times 10 volts, that is 80 coulombs. Your charge is in coulombs. Please make sure you take note of all the units. The moment your unit is not correct, you will not get your full marks. Your mark will be deducted. So your unit must be correct for every of your calculations. So for C2, excuse me, the charge for the second capacitor C2 multiplied by V, and our C2 here is 4 farad multiplied by our 10 volts. We have 10 coulombs there. For C3, we have Q equals C3 times V, which is 2 farad times 10 volts, which is 20 coulomb. Now the higher the capacitance, if you take note, if you check for the C1, which is 8 farad, the charge is 80 coulombs. For C2, which is 4 farad, the charge is 10 coulomb. For C3, which is 2 farad, the charge is 20 coulomb. Excuse me. It's 20 coulomb. So from our calculations, it shows that 8 farad, which is the highest capacitor there, highest value for the capacitor we are having, has the highest charge. So the higher the capacitance, the higher the charge. Now the last part of that question is getting the potential difference across each of the capacitor. Now if you remember very well, I've said it earlier that For a parallel combination, the same potential difference is what they have. They have the same potential difference across all the capacitors in that particular circuit, in that particular combinations, which is why the potential difference supplied to that circuit, which is 10 volts, is the same potential difference that will flow through all the voltages, all the capacitors. So for each of the capacitors, C1, 10 volts will be supplied. For capacitor C2, the same 10 volts will be supplied, and for capacitor C3, the same 10 volts will be supplied. And that is why it is said that V equals to V1 equals to V2 equals to V3 and equals to 10 volts. Now this now takes us to the second combination, which is a series combination of capacitors. Now in series combination, looking at what we have, it can be seen that the battery gives Q amount of charge. The same charge is acquired by each capacitor. And finally, the amount of charge is taken out to the negative terminal of the battery. Now, do not be confused by how this particular circuit diagram is being drawn. This one is just showing you that from the cell, from the V down, from the positive side of our cell, of our battery, that positive terminal, it is going through to C1. It means the positive side of C1, and the negative side of the cell as well. When you go backward anti-clockwise, goes to the negative side of the C3. They are just trying to show you the terminal of the capacitors with the positive and negative that is being drawn there. So do not be confused. What the diagram you are having there is the capacitor C1, capacitor C2, and capacitor C3. Now remember that it is only in parallel circuit that you have the same voltage flowing through, but in series the same charge. In series, the same amount of charge is being sent to all the capacitors, is being passed across to all the capacitors, unlike the parallel having different charges. Now, the formula for equivalent capacitance for a series combination is different from how it is being gotten for our series combination of resistor. So for series combination of capacitor, now what we'll do in getting our equivalent or total capacitance is 1 over C equivalent equals to 1 over C1 plus 1 over C2 plus 1 over 3 1 over C3, depending on the amount of capacitors we are having. And C1, C2, C3, C4, those are the capacitances that we have in the circuit. Now, sample problems on series arrangement of capacitor. The question says calculate the equivalent capacitance, charge, and potential difference across each of the capacitors. We have the first capacitor here to be 2 farad, the second one 4 farad, the third one 6 farad, and the potential difference across the circuit is 10 volts. So the first one to do here is equivalent capacitance for a series combination of capacitor. What we do is 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3. So you now had 1 over C equivalent equals to 1 over 2 because our C1 is 2, plus 1 over 4 because our C2 is 4, plus 1 over 6 because our C3 is 6. So by the time you find the LCM and do the normal addition, multiplication and addition there, we'll get our 1 over C equivalent to be 11 over 12. So since what we are looking for is C equivalent and not 1 over C equivalence, we now do the inverse of 11 over 12. So by the time you do the inverse of 11 over 12, you will now be having C equivalent equals to 12 over 11. So the CEQ, which is equivalent capacitance, will now give us 12 over 11. So by the time you divide 12 divided by 11, you'll be having 1.091 farad. So to get the charge across each capacitor, so the first thing we do is Q equals CV. But I need you to remember, always have it at the back of your mind, that for series combination of capacitors, the same charge is flowing through. When you have series combinations of capacitors, when your capacitors are arranged in series, you have the same charge flowing through. Now you have Q equals to CV. Now since we have the same charge flowing through, so there is no need of doing Q equals C1 V1, Q equals to C2. No, since you are having the same charge for all the capacitors in that particular circuit, so what we'll be making use is our C equivalent, the total capacitance. Now the total capacitance is what we got in our A question, the first question we solved, which is 1.091 farad. So our Q equals to 1.091 multiplied by 10, which is the cell being the potential difference being supplied to the circuit. So our Q now is 10.91 coulomb. Remember, your charge is in coulomb. Since the same charge flows through the circuit, Q equals Q1 equals Q2 equals Q3 and equals 10.91 coulomb. Now to the last question, which says the potential difference across each of the capacitors. From V equals to Q over C, V1 is Q over C1. We need to get C1, and for C1 we need to get potential difference for C2, we need to get the potential difference for C3. So V1, which is the potential difference for C1, is Q over C1. So we have gotten our Q to be 10 divided by 91 divided by 2, which is C1. So our answer there is 5.455 volts. You get your V2 to be 10.91 divided by 4, and it gives us 2.728 volts. Then you get your V3, which is equals to 10.91 divided by 6, because 1.818 volts. Now the potential difference across each of the capacitors must equal to the potential difference that is being supplied from the cell. And you remember that 10 volts is being supplied from the cell, through the cell. So by the time you add all your V1 plus V2 plus V3, it must approximately equal to 10 volts. So if you check what we are having here, the higher the capacitance, the higher the potential difference. So the higher capacitance, the capacitor with the higher capacitance, which is C, which one has the higher capacitance here now? I think that should be C3, which is having 6 farad. It has the lower potential difference. The higher the capacitance, the lower the potential difference. Now it says capacitor voltage ratings. The voltage rating on a capacitor is the maximum amount of voltage that a capacitor can safely be exposed to and can stop. That can safely be exposed to and can stop. Now remember that capacitors are storage devices. The main thing you need to know about capacitor is that they store X amount of charge. They store charge at a particular X amount of voltage, meaning they hold a certain size charge. So this actually means that we have different types of capacitors with different types of charge that it can hold. So you will see capacitors that can hold 1 microfarad. You see capacitors of capacity of 100 microfarad, and so on and so forth. And each of these sizes of the charge they can hold comes at a certain potential difference as well. Now, when choosing a capacitor, you need to know what size charge you want and at which voltage. That is it. So by the time you know what type of capacitor you need, what size. Do you need the one that will be able to hold like 100 microfarad? Do you need the one that will be able to hold a certain amount of charge? Eh? Maybe 10 coulomb charge. That is the amount of charge you want it to hold. So you need to understand the amount, and you need it at a certain voltage. So it will give you the opportunity to know the capacity of the capacitors you need. So capacitors voltage rating is not the voltage that the capacitor will charge up to, but the one it can, it can store easily. The one that it can store, that it can be exposed to and can store safely. That is the voltage rating. Voltage rating on a capacitor is the amount of voltage that a capacitor can safely be exposed to and can store. Not the one that it can charge up to, but the one it will be able to store. That when you expose it to, it will not affect it. Capacitors in AC and DC circuit. Capacitors rather. So we have capacitive reactance. Capacitive reactance is said to be the opposition to current flow in AC circuit only. Like resistance, just like the resistance, reactance is also measured in ohms, but just that the symbol is different. The symbol for the reactance is XC. So anywhere you see capital letter R, you know that is a resistance. But for reactance, the symbol is XC. Capital letter X with a subscript C. Then we can actually say that our capacitive reactance is a capacitor resistive value that varies with frequency. Also, capacitive reactance depends on the capacitance of the capacitor in farads, as well as the frequency of the AC waveform. And the formula used to define the capacitive reactance is given as XC. Now I told you the other time that reactance is, the symbol for reactance is XC. So XC equals to 1 over 2 pi FC. The F there is frequency, while the C there is the capacitance. So in getting your reactance for a capacitance, your capacitance is very important. So in some materials you can just see it as 1 over omega C. So if you are not given omega is same thing as 2 pi F. Omega is 2 pi F. So in an instance where the data given to you in the question is just the frequency, so instead of using omega, we use 2 pi F. So either 1 over 2 pi FC, or you see 1 over omega C. So we are still talking about the capacitive reactance. Reactance in a capacitance is SC equals to 1 over 2 pi FC, which is same thing as 1 over omega C. Now, capacitance in AC and DC circuit continues here also. I said it's XC, which is our reactance. Capacitive reactance is 1 over 2 pi FC. So, and I told you already that the F there is the frequency, which is in hertz. The frequency is in hertz, that is the unit, and the capacitance is in farad, just like we have rightly said before. And I also said that your 2 pi F can also be changed or denoted with omega, which is the angular frequency. So from the capacitive reactance formula above, it can be seen that if either of the frequency or capacitance were to be increased, the overall capacitive reactance will decrease. Since what you're having there is inverse, you're having XC equals to 1 over, so since it is inverse, they are not directly proportional, they are inversely proportional. So which says that if the frequency of the capacitance were to be increased, then the overall capacitive reactance will decrease. So if the one at the right side is increasing, the one at the other side will be reducing, since they are inversely proportional. So as the frequency approaches infinity, the capacitive reactance would reduce to zero, acting like a perfect conductor. And now this is a sample problem on capacitive reactance. Now this question says that a parallel plate capacitor was connected to a 60 hertz. So by the time you see a 60 hertz, even with the unit, it will give you what that value is. 60 hertz, that is frequency. AC supply was found to have a reactance of 390 ohms. A reactance of 390 ohms. Remember, I've already told you that the reactance is in ohms, just like our resistance. So 390 ohms reactance, that is what we have. It says calculate the value of the capacitor in microfarad. Calculate the value of the capacitor in microfarad. So it's in microfarad. Depth means that whatever value you are having, whatever answer you are having, you must take it to microfarad. And when you take something to microfarad, it means you have already divided it by 10 raised to the minus 6. That's the meaning. Now let's do this. From our x equals to 1 over 2 pi fc, what we are asked to calculate is the value of the capacitor C. So which means we are bringing the C as the subject of the formula. So by the time you make your C the subject of the formula, we now be having 1 over 2 pi f xc, which is the reactance there. Now we have been given the frequency and we have been given the reactance. So all we now do is C equals to 1 over 2 pi, the frequency, which is 60 ohms, 60 hertz rather, times 390 ohms. By the time you multiply all this together, our final answer in microfarad will now be 6.8 microfarad. I know some people might be wondering that how did we arrive at 6.8 microfarad? By the time you divide 1 by 1 over 2 pi times 60 times 390, remember that your pi is 3.142. So by the time you do the division, you'll be getting 0.000068006. So since our answer is said to be in microfarad, so it means that you take that to like times 10 to the power minus 6. And remember that 10 to the power minus 6 is micro. So instead of you writing 6.8 times 10 to the power minus 6 farad, you just say 6.8 microfarad. Can you see? Just very straightforward. Just make sure that you punch your calculator appropriately, accurately. Now, the formula for equivalent capacitance for a series combination is different from how it is being gotten for our series combination of resistor. So for series combination of capacitor, now what we'll do in getting our equivalent or total capacitance is 1 over C equivalent equals to 1 over C1 plus 1 over C2 plus 1 over 3 1 over C3, depending on the amount of capacitors we are having. And C1, C2, C3, C4, those are the capacitances that we have in the circuit.